Ryan and I will be discussing about how Twitter fused Elasticsearch with neural networks to identify personal data. Before we dive into the work itself, a quick introduction about the speakers. So hi, I'm Rakshit Wadhwa, the one on the right, and I'm a senior software engineer at Twitter. I have been working at Twitter since past 3 years now, and I'm part of the privacy platform team here. And we build tools and services for data protection and privacy. Along with me is Ryan Turner, the one on the left, and Ryan is a senior machine learning researcher at Twitter. He has been at Twitter since past 2.5 years now, and he's part of the Cortex team. Cortex team provides machine learning solutions and expertise for various projects across Twitter. So let's begin with an introduction about what are the problems that we are trying to solve here. So the main problem that we are trying to handle here is the accounting for the personal data in various Twitter systems, and then tracing it how it originates and flows through various Twitter datasets. The problem is complicated because of the microservice architecture across the company. This leads to distribution of data across different teams and services. As a result, the accountability for the data privacy is distributed throughout the organization. To understand the distributed data, we need a common language or a taxonomy to refer to the data columns. We call tagging of these data columns with the standard taxonomy as annotations. The two main challenges in tracing and accounting personal data are, first, the data is continuously growing and getting distributed to various datasets and storage systems. These datasets and storage systems can be very non-homogeneous. Second, the data privacy and governing policies are continuously evolving, and Twitter as an organization needs to adhere to these ever-changing policies. Keeping these challenges in mind, we started with the following goals. Primarily, we wanted to understand what data exists in our systems, the sensitivity of that data, and the purpose for which the data is getting used across Twitter. Our secondary goal was to utilize this data to optimize our storages, understanding the usage pattern for different datasets, and to improve overall data security and data handling situation. The ideal solution to solve such a problem could have been to use a standard taxonomy within the schemas themselves. That is to name the columns with personal data directly from the taxonomy. This might have worked when you are building something from scratch, but changing schemas for the existing dataset would not only lead to heavy refactoring across the consumers and producers of the data, but would also be a long and painful process, which might even result into downtime for different services. And above all, this could have been a very error-prone and manual process. Now, coming to the solution that we actually adopted, instead of changing the column or field names in the dataset schemas directly, we decided to tag or annotate the columns with certain terms, and these terms come from the standard taxonomy. This has multiple benefits. It is done on top of the datasets and hence doesn't need any refactoring of the actual datasets themselves. This also means no downtime for the existing tools and services. Further, the design allows changing the annotation or adding multiple annotations to the same field, which would not have been possible if we made the changes to the schemas directly. This also means that we can automate the annotation process to a major degree by building a recommendation service for the annotations. So to make the annotation process easier, we built a recommendation engine based on probabilistic model on top of Elasticsearch. Now that such a system is not only useful for any company handling a lot of personal data, but also for any time you need a text-based lookup within a quantified uncertainty. We'll go into much more detail about the recommendation engine as the second half of this presentation. To make it more concrete, here are some annotation examples. Let's say that we have a dataset named profile that has a column called ID, which has a column description as unique identifier for the user. Here, this column is annotated as user ID, and in the absence of the annotation, it is very tough to determine what exactly does this ID mean for this dataset. Another example could be a dataset called timeline, which has a column name called user ID, which actually stores the Twitter handles and hence is annotated by username. Now the column name is user ID in the schema. So overall, an annotation recommendation service not only increases the development velocity, it also helps to maintain the quality of annotation through benchmarking and auditing previously annotated data. Here are a few numbers to understand why we need a recommendation engine rather than manually annotating from the scratch. We have 504 terms in our standard taxonomy. We call these terms personal data types. There are more than 2 million fields or columns spread across more than 100,000 datasets and a dozen of data stores. These 2 million fields needs to be annotated with these 504 personal data types. When dealing at this scale, having a recommendation engine for these personal data types can be very helpful. Now, a quick overview of the recommendation engine before we go into more detail. Twitter manually created a taxonomy of 504 possible annotations. The taxonomy was created by combined efforts of engineering, product management, and legal teams. Engineers and product managers then used this taxonomy to manually annotate datasets for a while. Around 30,000 columns were annotated this way. Then this became a basis for creating a recommendation engine, which was used to annotate over 2 million columns spread across 100,000 datasets, and these were annotated to these 504 annotations. Note that the final annotation is still done by the user, as these annotation needs to be accurate due to various privacy and data governance policies. And now, quick overview of the high-level architecture for the annotation recommendation service. At the bottom is the data collection engine that collects column and personal data type mapping, as well as other metadata about the datasets which are already annotated. This essentially acts as a training dataset for the recommendation engine. The recommendation engine is based on a probabilistic model on top of Elasticsearch. And the recommendation engine interacts with our internal services and tools through the REST APIs. These REST APIs integrate into our tools like metadata stores, code review tools, linters, etc., to make it easy to annotate the new data as well as search for already annotated data. I now hand it over to Ryan to give a deep dive into our recommendation engine. Over to you, Ryan.
Hello, I'm Ryan. I'm going to talk about the ML specific parts of the system now for our automated recommender. So the first part of any ML problem is to frame the problem. So here we're trying to build an automatic data annotation system. So the first step was to get some ground truth labels as to what are some examples of labels that we can trust. So we have quite a large data set of annotations, yet only a subset, about 70,000 of them, were used as ground truth because we only subselected ones that we trusted would be accurate ground truth. So the basic setup of the system is to take a variety of inputs, and we used metadata on every column, such well, name of the data set, name of the column, and then descriptions for these that are sometimes written in as metadata. And these are all concatenated together as a big feature vector of unstructured text, basically. And then they'll be used to predict a label of one of the 500 different types of annotations. So this is basically a classification problem, and with an interesting feature space because it's this unstructured text. So representing that same slide from before in a more diagram form, here are some examples of classifications of a few different annotations. So here we have the user ID and username are in bold. This is in the bold side on the right. It's the side we are trying to predict. So user ID and username are examples of different annotations. It sounds redundant, but they're actually not the same. And here, these are the features. So we have a name of the data set, which is say timelines. And then of course here we name the column user ID, but of course it's very subtle because the actual true label in this case is user name, not user ID. And then here there's a description, which is Twitter handle. And this is sort of the clue that the system might be going off of to determine that it's a username instead of user ID. So these text features on the left are what the system has to go off of to make a prediction. And then some of the labels on the right under the annotation column are examples of the labels we're trying to predict. And these are all part of that list of 500 different annotations. So we have a closed set of possibilities for the labels on the right, whereas on the left, these can be just pre-open-ended text for the possible input features. So we wanted to use systems that were um, already built, try to leverage existing systems so we didn't have to reinvent the wheel at all. We made the choice in this particular case to use Elasticsearch, um, which is a system for uh, retrieving documents based on a few keywords that may be similar to things in the documents. Um, so basically, we needed to do a reduction, and in computer science terms, here we need to do a reduction to convert this classification problem to the document retrieval problem that Elasticsearch solves. So basically, every single annotation had to become a sort of document, and then we would do queries at test time. So basically, we'd sort of concatenate a lot of training examples together as documents. We'd also do a couple variations of different types of queries because Elasticsearch allows for different types of queries. So we applied a few different variations. And then finally, we needed to train a model that would take these multiple confidence scores and convert them to a single probabilistic prediction. So we wanted to get a probabilistic classification over the 500 possible classes because Elasticsearch only outputs uncalibrated scores, not probabilities. And of course, we did multiple queries, so we end up getting multiple scores. So we can't even sort them. So we have to convert them all into one probability was the goal. So here's how we converted the uh, classification problem into an Elasticsearch problem. So basically, if we look in the training set for username, we take all the different examples where we have usernames to correct the annotation. We can take all the cases where those are column names of those training examples, the descriptions and everything, and we can just concatenate all those training examples together using commas, and then each of these becomes sort of synthetic documents that are fed to Elasticsearch. So here, for instance, column descriptions, this is this concatenation of a bunch of training examples, but this will become the document for uh, for username. And then at test time, if we enter the column description for a new column we're trying to annotate, and Elasticsearch returns this so-called document under the concatenation of column description, then we'll say that username is the correct annotation for that test set column. Finally, there's also the calibration phase where we wanted to convert that to probabilities. So we used standard offline calibration methodology. We use a held out set to take the uh, output score of Elasticsearch and then fit a probabilistic classifier to convert the output of Elasticsearch to a probability. And this is done using a held out 20%. So we're not recycling the same data that was used to build the Elasticsearch index. Otherwise, we would be getting biased probabilities. The model would be overly confident if we were recycling the same probabilities. And we also, because we do multiple queries of Elasticsearch, the calibration model actually also has to combine multiple scores. So if we do 5 different Elastic variations on Elasticsearch queries, we'll get 5 uncalibrated numeric scores, which then all have to be merged together into a probabilistic model, into probabilistic prediction. So we both have to convert the 5 scores to 1 score for particular annotation, and we want it to be a probability. And then this is just a diagram representation of this, where we make n different Elasticsearch queries for a particular test case. We get n different response scores R, and then we'll feed it. In this case, we ended up feeding it to a neural net model to combine all those to one probability as the output, whereas R's are just arbitrary scores. And we compared various different systems for this, and as a different just generic classification systems. So we evaluate it both on the top 10 accuracy, where higher is better. So this is the true answer within the top 10 recommendations. And we also, to evaluate how well we're calibrating the uncertainty and our confidence in the predictions, you can look at negative log likelihood, um, which is also known as cross entropy in the deep learning world, or perplexity in topic models. It comes with a lot of different names. And we can compare this as well, and this is a loss function. So uh, lower is better in this case. And on both these, there were definitely a few different high performing choices of models to choose between, but the neural network architecture that we evaluated was somewhat better than all the other off the shelf methods. So we ended up going with that. So we didn't just use the neural net because it's a fashionable thing to do, but because it is, is the best from our evaluation. And almost 3/4 of all data sets, when we deployed it internally, ended up being annotated using this tool. Just at least for some of the columns, they ended up with recommendations. There's a minority of users who are so confident in being able to do this manually that they don't really even need um, automated recommendations. But as we found out from our analytics, that the majority of internal users for data scientists and practitioners uh, just needed some help. They used the recommender tool because there's definitely a lot of obscurity to getting a lot of these recommendations right. So in the conclusions, using machine learning models to help a recommendation system to annotate all these old data sets was a very useful exercise in getting everything involved in this standard taxonomy. There's a lot of work that had to be done, a lot of work to clean up a lot of legacy data set problems, and this effort, this product we developed here, really helped accelerate that process with less man hours. And we see that 75% of the data sets internally ended up being annotated this way, company wide. Um, and this will help in any other use cases as well for data auditing and handling. And that I will. Thanks for watching.